Hello, everyone. Thanks for joining me today. The topic of my talk is SQL Server Index Evolution, welcoming vector indexes for AI workloads. Um, I'm really excited to be talking to you guys today about this topic. For me, well, I'll just go ahead and go to my next slide and show you. For me, I'm in the role of an enterprise architect. I work for the city of Gresham, Oregon, and in that role, I do a lot of work to, digitally transform the technologies that we're using, from our data footprint to our development efforts to, connecting across SaaS products and leveraging all sorts of cloud platforms and different types of services. And yeah, you know, uh, since AI is the Katamari that's kind of sucking up the whole world as it rolls around, it of course is on the city's radar, as I'm sure most larger organizations are looking to figure out how they can use AI. And for myself, things really started to become real, maybe in the Fabric area, but especially with SQL Server. For me, I'm a huge SQL Server buff. See if I can get this to show here. It's been gone. T-SQL fundamentals. Reading that, it really helped me understand SQL Server is a really foundational technology, and it's one that we're able to trust. It's able to provide like reliable data access, and it prioritizes that above all sorts of different types of technologies that are out there. And the way that AI gets implemented oftentimes is a standalone service, something that could just be used, right? And so for me, when a capability becomes a part of the SQL engine, that's kind of a signal to me that, well, this is just business as usual now. And the way that vectors, vector embeddings, and vector indexes have been implemented within SQL Server, uh, I think has a great story about how it really looks a lot like the rest of the data types and the indexes that we're already familiar with. And so I wanted to use this as an opportunity to kind of talk about, what are our existing index types? What do vector indexes look like, and how do they fit together? And so we'll go ahead and go through that today. Here, I got the goal at the top and the three topics that we're going to go through. And I do just want to mention, right from the start, that some of these concepts can be complicated to think about and talk about, but I really want this specific talk to be fairly simple. Like I mentioned, I want to be able to relate how this is a part of SQL and how it's just another thing that we can use. And I also want to kind of highlight how some of the theory behind the SQL we're used to compares to the theory that's behind some of these new SQL capabilities. And I'll try to keep it simple, and then we'll go through some demos. And I just want to point out, I don't work for Microsoft. I'm a SQL Server user, and my need to understand how SQL Server features come out and how to use them are what primarily motivates what I learn and what I want to share with all of you. So, if anything I say or anything I show isn't clear, or you actually like have like an interesting perspective you'd like to provide, please do feel free to do that, because I use these opportunities to learn myself. So just diving right in, you know, let's stare the complexity of AI vector indexes right in the face, right? And before we even go down the AI path, like let's stare the complexity of indexes in the face. Like I mentioned, that SQL Server is based in operations that we can trust. You hear about the ACID properties. Those things are driven by a mathematical foundation. I've got some formulas over on the right. One of the things we're going to talk about as we talk about the most popular indexes are B trees or B plus trees in the world of SQL Server. And those are mathematical algorithms, right? And so that's how you're able to have like trust and guarantees around SQL Server operations, because they've actually been mathematically worked out beforehand and those algorithms get implemented into the technology, right? And so, conceptually, let's just like answer the question, what is an index? Well, an index is a data structure. It's a piece of data that lives in your SQL Server, but it's not meant to be the data itself. It's meant to be leveraged by the SQL engine to improve the way that data is accessed, right? So we're kind of starting to talk about pointers and stuff, but we're also maybe talking about the way that an index might inform how data gets organized actually on like the disk, onto data pages. And so conceptually stepping back, if you think about like what indexes do, they take certain pieces of data that may not look numerical and they translate them into numerics, right? They translate them into these algebraic structures, these B trees. And so that translation already exists in SQL Server. And that's what we're going to see as we talk about vectors is that's exactly what we're still doing. We're talking about parameterization. We're talking about taking pieces of data and translating them into some sort of numerical format that the engine knows how to work with. And in the vector case, we're just happen to be talking about a high dimensional geometry. And I'm going to try to talk about like the evolution of indexes and why like the classic index problem isn't able to really solve that semantic search without high dimensional geometry. So just reflecting more on indexes, database indexes, they're a little bit like the index at the back of the book, right? Or if you think of like any sort of like lookup where you need to go try to find where something is at. You may have like a table of contents or an index, and it tells you what page a concept is on. And these pages, like that's a pretty fundamental concept within SQL Server itself, because if you're familiar with SQL Server, you've got your MDF file. That's where your data lives. Within those MDF files are what are called pages, right? And the data itself lives on the data pages, and it has to go in there in like a row store. At least traditionally, that's how that happens. And these data pages store information to try to help operations accessing it with tricks about like offsets and whatnot. Because if you think about like an application that's submitting data one by one, piece by piece, it's not going to have like a guaranteed sort order, right? And so if you would then need to do an operation that's going to go in and find a specific piece of data, well, it would help, one, if the data was sorted in a specific order, so that way these offsets actually could make it easier to look at clusters of records as opposed to having to keep track of each individual one. So, without that, we're talking about a heap, right? And so that is like what all tables in SQL Server start at. If they don't have an index, it's considered a heap. And what that means is like things just go in one at a time, really fast, but might be very difficult to find something in there. And so that's that concept of a full table scan. If you don't have an index, you'll end up with a full table scan. And we'll try to show that off in some demos if we have time. But ultimately, what this is going towards is our SQL Server index types, right? Like why, or like now we know why we need indexes because data without some sort of structure or some sort of like pointer to where all that data is at, well, we need something to improve that data access. And so here are like the four major big named index types from SQL Server. And we're going to go through these one at a time. So clustered index. This is, you could say that like clustered and non-clustered indexes are the most important indexes in SQL Server. They've been around the longest, and they kind of serve two distinct purposes. And if the difference has never really been clear to you, I'm going to try to use these visualizations to show the main difference. So first of all, clustered indexes, they actually determine the physical order of your data on the disk, on your data page, right? So when you declare a column as a clustered index, that actually begins an operation within the SQL engine to rewrite your data. So this idea that within the structure, this index page is pointing to the data itself, and the data lives within the structure. That's kind of why it's called a clustered index, because within this index page, there are records that say, oh, are you looking for, let's, say we got a customers table. So maybe because this actually physically will sort the data, if we make a primary key on that customer ID, you're going to get like 1 to 6 here, 7 to 8, or 7 to 10 here, and so forth. And then your index page, it can do something really smart, where it doesn't actually have to store information about where every single row is. It can just store information about what memory position your ranges go to, right? So that's the concept of the cluster, is that this index might say, oh, rows 1 through 6 are on the first data page. It points to that whole cluster of records. And so this is really ideal for primary keys, of course, because it's actually physically changing how data is structured on the disk. And so you don't want to do that a lot. You don't want to change the clustered key. And you can kind of think about this not necessarily as that back of book index, but more as that table of contents, because it's storing that data really smart in a way that says, I know that this data page starts with this customer ID and it ranges through, so many. And so if I need to find a customer ID in that range, I can go directly to that data page. And this concept of leaf nodes, or the leaf level here, so that's the key thing to remember about clustered, is that it actually changes this data on the disk, and that data is a part of your structure, of your index. Now compare that to a non-clustered index, and I'll flip back and forth real quick on to visually notice what changed here. So I kept mentioning that the data lives in the leaf level. For non-clustered index, the data does not live in the B+ structure at all. The thing about a non-clustered index is that it's called non-clustered because it's not pointing to like a range of IDs that exist on a data page. It's actually making specific row identifiers that go in and point to a specific data page. And it doesn't live, the index doesn't live with the data. It lives separately from it. And it doesn't order the data on the disk. It's just storing these pointers to where the data is, right? And so it's kind of conceptually used differently than a clustered index, where a clustered index is really great for those range queries. Now in the non-clustered, you're talking about the other columns that may not have a great sort order. And so you need to store like a record that says, oh, if your where or if your where clause is going to filter on this column, it would be great to have a non-clustered index on that column, because then I don't need to go do a full table scan to figure out which rows will pass that filter. Instead, I can look to my pointers to go right to those. So maybe from a high level, all of that can seem confusing. And if so, I'm happy to kind of talk more about it. However, the main point I want to make here is that there are these algorithmic structures behind the indexes, that there's this mathematic basis behind how our classic clustered and non-clustered indexes are created. And the same is true for our other ones too. So we've got the column store index. So I'll just briefly talk about the column stores because it's kind of an interesting use case here. So column store indexes, conceptually, they're different from the clustered and the non-clustered, which are row store indexes, right? They physically store your data in rows. They talk about, I can see where the data is in the row. In a column store index, we're actually talking about making it in a non-clustered instance. We're talking about making a new data structure that is going to have the data, instead of it living in that B plus tree structure, now we're going to have it go through a couple processes that allow us to basically compress and segment the data so that way we can query single columns at a time. And the reason you do that is because for analytic workloads, you really rarely, you're mostly trying to answer questions about data in aggregate, right? And so you're not needing to seek for a specific record, and you're usually not trying to answer a question about every column in a row. Instead, you might be asking a question about a single column, like amount, right? And so it makes sense, instead of when you have to query your data, to say like, select some amount from table where blah, blah, blah. Instead, you can just say some amount, right? And because we have taken that amount out of its row store, made it a column segment, and then compressed it so that way, if there are repeating values and stuff, we're not actually storing those over and over and over. We'll just have a dictionary or like a run length encoding that's able to tell the engine, using this column store index, what value it should return. And so for these things, this is a little bit like a process here, where those row groups, what is that information, the column segment, that information, and the compression, that information is kind of what's going into your LOB page, your large object binary page. I may have just misspoken there on that name. I think that's it though. But basically, like within there, you can think of that as like having a bunch of dictionary lookups, right? Like a data stream with dictionary lookups, that when you say like, find me an amount for this column, it's able to use those dictionary lookups rather than having to go read each row one at a time. So the theory behind some of this stuff can be kind of complicated. There's a really great video I'm going to post in the chat right now to try to help with this stuff. Oh, I closed it. So I'll get that in just a second, actually. I think it's right here. Yeah. So I'll drop this in the chat for you guys. And I promise, like, a visual explanation of this is really the way to go. So this one is clustered and non-clustered. And this one's the column store. And I'm going to have some other videos for you guys when we get to the vector indexes and stuff. And yeah, I think rather than recreating them here, take some time. Each one's only 20 to 40 minutes. It really goes a little bit deeper into all the stuff I just said and breaks it down one at a time. But I want to get to vector indexes here, so I don't want to spend too much time on column store and even clustered and non-clustered, but we'll look at some code for them anyways. But last index here, full text search index. And I think it's important to pause for a moment on this index, because it starts to get at the heart of why vector indexes, vector embeddings are needed at all, right? Because the full text search index, it was SQL Server's attempt to actually enable similarity searching, but it's not approximate. It is exact. It has mathematical guarantees, and so therefore it can't do some of the same semantic search capabilities that come from our new LLMs that are creating embeddings probabilistically. That's not what's happening in the full text search index. It's using technologies that did go on to inform how vector embeddings are done, like tokenization, but it creates what's called an inverted index. And I have that kind of trying to show here. And it's called inverted because it kind of changes the idea of, instead of storing information first about where data is, let's store information starting from the tokens, right? And so the positions in here, you break your data down from a row store, you find its term, you relate to its doc ID, and you say where those positions are within the row store. And that's how like a full text search index is able to do something like the like command, but the like command actually does use a B+ structure because it's using the classic engine, whereas the full text search engine or index, it's actually using a whole new engine, the full text engine that had to be created. And you have to have a provision server, for example, to be able to do that. So you can't run it in like the serverless options, and that's what I'm going to use for my demo. So I'll show you some code for it and whatnot, but basically, I think the important thing to keep in mind here is that because this is still kind of operating not at a high dimension, so it's only able to kind of look at words one at a time. It doesn't look at sentences. It does not portray meaning at all. That is all coming later with the vector embeddings. And so it hits a hard ceiling about even if we threw more GPUs and more data at it, the full text search index is just not designed to be able to answer questions about meaning. So if there's a misspelling, that's not going to work, right? Um, so we'll keep going. Okay. Yeah, I think let's go ahead and just like quickly look at some examples of our classic indexes here, right? So I've got two things open here. I've got my Azure SQL database open, and I've tried to create some stuff for us. So for example, our I've got some Olympic data. This is from a Kaggle data set. I figure it's the perfect time to talk about Olympics, right? So what we can do is take a look at these in SQL Server, like always. And we can see here, this one, for example, it has no keys. It's just got these. We can do a quick select on it. So this is a heap, right? And so if I do a where on here and I enable my execution plan, I'll just come down here and we'll just grab just some random name. You can see we did a table scan, right? So that's what I was talking about with the full table scan. Okay. So that is on athletes. And so I've got this example here of doing it on metals. So let's go ahead and do that. Blah, blah, blah. Okay, so I didn't do it on athletes, I did it on metals. Hopefully this is big enough to see. I know that they changed the ability to zoom in the latest versions, but not over here in the Object Explorer. So we still don't have that, as far as I know. But yeah, so here are our columns. Oops, this is wrong. Olympic medals, here are our columns, right? So I've just added a primary key or a clustered index on my primary key, right? And so what that means now is if I do that same select that I'd done before, except this time we'll do it on medal ID. And also, I'm pretty sure in the last one I did it on the athlete name, which, that wouldn't be what I was going to use the primary key on anyways. I would use the ID. So this is maybe a little bit better. I just need a random medal ID here. Okay, yeah, they're all assorted, so we can just set 302. I don't know why. There we go. Yeah, I wanted to do that. Okay, and so now you can see because I'm using a column that I defined this index on, instead of doing a table scan, now we're doing an index seek. So the execution plan here is kind of proving that we're able to improve our query here. And similarly for a non-clustered index, let me try to actually grab all three here at the same time. Here we were talking about that clustered index. Leave my variables. think I can do all of them at the same time. Doesn't seem like it wanted to keep that there. Well, anyways, we'll look at the execution plan here. So because I created the primary key, it was able to do the clustered index scan on there. So let's try it on the raw Olympic medals. There we go. Got to do the table scan. If it's got a primary key on there, it's going to find a way to use that. But we can give it even better information than making it use that medal ID, because that's ultimately not what I'm trying to filter on in this next one. I'm trying to filter on these 3 items here. And so when I create that non-clustered index, I can specify what those are on, and I can even say columns to include, so that way it doesn't have to go back to the row to get that information in a query. So for example, the medal type and the athlete name in my query here. So let's go ahead and create this. Okay, do a quick refresh. This did so because the non-clustered, it doesn't recreate any data on the disk. It just adds a new data structure that points to where the data lives on disk. And so now when I run this, I can actually remember everything I need. You can see that now we got this non-clustered index usage, right? So this is nothing like breakthrough or nothing like crazy here. I'm just showing very simply, you're in SQL Server, you're using indexes, you can see use this execution plan to kind of see how including an index affects the performance of your queries. And introducing clustered and non-clustered indexes and even vector indexes will impact this execution plan. Okay. So moving right along, I've got the code here to kind of keep showing some more examples, and then even show with the column store index. And again, we're talking about aggregations for column store, so you really want to be able to try to find your columns that are, I'm still in the wrong area here, aren't I? No, here it is. So basically, like by specifying what your columns are in your index, that's like what you're promoting forward for your column segmentation, right? So basically, these columns are going to get broken out into those individual columns, and they're stored in the data pages separately, right? So that's why it's a non-clustered. If this was clustered, this actually does work with column store indexes. A clustered column store index will change the order of your data on the disk, right? And it will also, because you can only have one clustered index, it means you're going to have to remove your primary key as well, right? And so a clustered column store index is a special case in my mind. And if anybody has like a specific reason to use one, love to hear it. But for the most part, what I see is most common is to create the non-clustered column store index, which basically just allows you, like another non-clustered index, like a row store. Row store is the default. Like you can have multiple of them on the table, and they live next to your data, so it's not actually rearranging it. So non-clustered, the way to go to there. And then for full text indexes here, like I mentioned, you need that full text catalog. So I'm not going to be able to show this stuff without having a provisioned instance, which I just don't want to environment switch during the demo. So but it is just like any other index, even though it's using that other engine. Okay. So we're about to get pretty quickly into starting to work with some vectors and embeddings. And to get there, I just want to take a moment to reflect a bit more about why they're important, right? So we talked a lot about how our traditional indexes, they're solving specific problems about how to access the data, right? Whether we're trying to do it from an arranged query to use that clustered index, or maybe we're trying to use it in a predicate, so we make the non-clustered index, and so forth. So for the vector index, right, it has been created specifically to be used on vector embeddings. And it uses what's called a nearest neighbor search in order to figure out like which vectors in these embeddings have actually, are actually the closest to it. And so in that way, like you're storing that information about that semantic similarity, right? So that's what the index is able to add. And we're going to talk a little bit more about that. And I even want to try to help conceptualize it a little bit. But first, I just want to like put it in the historical context of like, we've talked about the evolution of traditional indexes. So vector indexes, they kind of have their own story here. And they're also rooted in mathematics, which is nice that this is just a continuation. This is just business as usual for SQL Server. Because in the same way that linear algebra and like set theory are powering SQL engine regular database operations and indexes, linear algebra and by an extension with calculus, like the concept of neural nets, are what have enabled vectors, right? And so I have this really short timeline here to talk about how, linear algebra, that's where the term vector comes from. We're talking about vector transformations. And as we move into like neural nets and talking about LLMs, talking about matrices, and that's when a vector becomes a matrix, that's when it's actually going into those higher dimensions, right? And so this story on the left of what happened before like 2010, it was this idea of trying to, like what I said at the beginning, of translate like language, just any type of information, into geometric meaning, into some sort of algebraic structure. So same thing that's happened with other indexes happened with the vector index too, where we're just talking about trying to translate information into something a computer knows how to do really fast. And a key that we'll see that like makes all this like possible is the neural net, because basically conceptually, if you in any of these algorithms, you're like kind of starting at this random point, you're going through this process of calculating a loss function forward and then backward, and that's called training the neural net. And when you do that, like on like language, for example, that's what the equivalent of learning is. And that learning is what's able to project that semantic similarity. And I've got a couple abbreviations: VSA, LSA, IVF. Those are like really early versions of trying to do what vector indexes eventually did in higher geometries. And in the 2010s, the vector embeddings start to come into their own. And this concept, this thing called word2vec, started to make it really easy for anyone to start to create vector embeddings, right? But they were still really basic and didn't really operate in high geometry, as high geometry anyways. And but it makes it a great basis for a conceptual demonstration, which I'll do in a second. But because of those limitations, right, we had to move into something less exact, into something called approximate nearest neighbors. So that ANN. And that's kind of that concept of, if we have too many vectors, you can't calculate the closest neighbor for every vector. And in fact, what we'll see in SQL Server is that over 50,000 vectors, that's where you need a vector index. And under 50,000, SQL Server can actually just calculate those exact distances for all 50,000 vectors when you do your query. And that's embedded in something called the vector distance function. But when you want to use vector search, you actually need to do this approximate nearest neighbors. And we'll see where that's baked into SQL Server a bit more. All this started to really heat up when Google released the paper Attention is All You Need. It revolutionized with this idea of transformers, which basically is just like we're stacking algorithms we're stacking neural nets now, and we're focusing, each component is just doing a specific individual thing, and the attention on the lower layers within the neural net is what's able to create a transformer. Why all that matters is because that's kind of like what makes vector embeddings possible in high dimension geometry. And we came up with these concepts of the hierarchical navigable small worlds, and the SBERT, and FAISS. And these are vector embedding models that were able to come out of this work of basically linear algebra, neural nets, vector embeddings, right? And now in today's world, we've seen the rise of vector databases. We've got like Pinecone and Chroma. Postgres got PG Vector pretty early on. Azure, even before SQL Server, they created something called Azure AI Search, where you're able to store your vector embeddings in there. And there's actually a really still a reasonable story for using that as a vector store, and it is kind of more of a classic model. However, we love SQL Server, and obviously, like my whole point of doing this and is saying, this is business as usual. Vector embeddings are just data. Where does your data go? It goes in SQL Server. So, we continue down this path of semantic search evolution. Now we've got the LLMs, we're able to do RAG, and we have agents, but all of this is just built on this mathematic technologies that have been moving forward. And so I'm going to bring this onto the screen. This is a video here to help conceptualize vectors. This is from the Word2Vec era. This is absolutely not how things work now, because as you can see, I've only got 3 dimensions here, right? But I really like showing this off because, it really just kind of goes back to that point that we're talking about linear algebra. Vectors can have simple mathematics done on them, like addition, multiplication. You can do like cosine functions, and those are exactly those basic vector transformations are how vector embeddings are created, and also in some cases how the indexes perform the nearest neighbor searches. So I've just got a simple example here where we're just going to use 4 concepts, right? So it's kind of the idea that Paris is to France as Rome is to Italy, right? They're both the major cities within those 2 countries. And so if we were to vectorize, create vector embeddings from France and from Paris, it might look something like this, right? We're just talking about some simple vectors. And similarly, we might do the same with Italy and Rome. Okay, and so now we've just got our 4 regular vectors here. If we did basic vector transformation, like taking Paris minus France, right? So we've taken this vector and we've subtracted this vector. That ends up with this. Now its tail is still at 0, 0 because we're just doing a regular vector subtraction here. But if that difference vector of Paris minus France, if we were to add that to Italy, well, suddenly when we move the tail of Paris minus France to the head of Italy, Italy plus Paris minus France equals Rome. So again, not at all how a vector embedding looks nowadays in high dimension geometry, like what we'll see in SQL Server as we try to view them out. It'll print it out in JSON, and you'll see it's got many more dimensions. It's every one of those commas, every value after the comma is going to be a new dimension. But hopefully this kind of just makes sense that vectors, we're talking about transforming meaning, semantic meaning into geometric meaning. And once it's in a geometric meaning, math takes over, and it doesn't even matter that it's words anymore. It's kind of a really cool trick, and it's the basis of why language services work at all nowadays. Okay, I'm going to take a quick break for a drink. Let me know if you have any questions. All right. So now we've understood why vector embeddings came about, how the technologies that produce them. Let's talk about the indexes, right? Because if we're talking about doing that similarity searching between Rome and Italy and Paris and France, those vectors need to live somewhere, and the distances between them basically get stored somewhere. And so the classic example before what SQL Server chose to do, and even before what I mentioned a moment ago, the hierarchical navigable small worlds, was this thing called the inverted file index. And an inverted file index, basically, it's doing that thing I mentioned where it's actually flipping it on its head and it's saying, okay, let's look at the words that are in here and let's see if we can group them, cluster them into specific like segments here. And so you end up with these centroids of your clusters. And then if you're trying to find the similar vector, you just have to figure out which centroid it's in, right? So an issue here, though, is that if you have 2 points that are close to each other, but a part of different centroids, that type of index is never going to be able to return that. Instead, it's going to say that it's a part of this one, and so therefore all of these vectors would be returned as its nearest neighbors. And again, that's what we're talking about with a vector index here, is we're talking about a way of storing something that helps our SQL engine find the data on the disk, right? And so that index is storing information about the nearest neighbors. So IVF, kind of an older technology. Next, we move to the hierarchical navigable small worlds, HNSW. And this is also not what SQL Server is using, but I think that conceptually it's the next important step. And it's based around this idea of a skip list, right? And so just in the same way that these mathematic tricks help things like the column store, not have to do that run encoding and not have to like look at every single row, or the same way that a clustered index is able to only store the ranges. So that way it doesn't have to store every single row. The HNSW's idea is that if there is data that's not relevant between 2 nodes, you can just skip it, right? And the reason that matters is because if we try to go into try to do that IVF that we were looking at a second ago, right? It wouldn't make sense to go to every single one of these. And also our vectors aren't in 2 dimensions. So that is why we get this navigable small world where basically you go around and you look at the vectors that are closest to your query, right? But we also need it to be in higher dimensions. And so that concept of we're just going to start at a random point, we're going to query each vector to see which is closest, but the reason it's called a hierarchical navigable small world is because we drop down in these layers. What we're forming here is something called a graph, where your data points are stored as points, and the relationship, the distances between them are the nodes between the points that connect these points, the nodes of the graph. Or sorry, I mean the edges. I said node twice. The vectors that connect the nodes are the edges. And so trying to do it all in just like 2 dimensions here doesn't allow us the speed that the hierarchical navigable small world does. Now, HNSW is also not what SQL Server uses. It uses something called the disk ANN. And I'm showing this progression because disk ANN is really kind of that latest idea of how do we store this information about vector relationships. The biggest revelation about disk ANN, the reason why it's needed over the HNSW, is because the HNSW, and this is like optimized for in-memory operations. So you're talking about having huge amounts of RAM to be able to store this, essentially this graph of all of these data points. But that's not the way SQL Server works. SQL Server stores its data on disk, right? And so because the data is on the disk, you can't count on it all being memory in the same way that you do in HNSW. So this thing called the Vamana graph, and I wasn't able to really find a good, what I thought was like an actually explanatory way of visualizing this. But from what I understand, it kind of goes away from this idea of having multiple layers, like the way that the HNSW does. But its motivation is still just about trying to solve the problem of how do I store my nearest neighbors, information about the nearest neighbors to each vector. Okay, I'm just looking through my notes. See if I missed anything I wanted to mention. Yeah. Okay. So we're going to dive into looking at the vector codes, how to get started in SQL Server to do it, the T-SQL code. But, even if you know how to create a vector embedding, and even if you know how to create the vector index, like why is it useful, right? And a promise of this talk is we're going to talk about how vector indexes power AI workloads. And so this is kind of it from start to finish for like your just basic chatbot instance here, right? So first thing you have to do, embed your data. So those embedding models, that's where like your multimodal models, that SBERT comes in to be able to break apart all of your sentences, tokenize it, transform it into vectors, return those vectors to you. You get your vector embeddings, you store them in SQL Server. Create an index specifying a distance metrics like cosine or something like that. That distance metrics, actually, so now you're storing the information that you need to be able to identify your closest neighbors. And when you do a query using vector search, you specify how many of those closest neighbors you want to return. So once you've got your vector embeddings and your vector index, you're ready for it to be used in an application, right? And so your chatbot application, basically the way it works, this is the basis of all RAG systems, is that you take your user prompt, you create an embedding off of it too, and then you compare those embeddings to you run them against your vector index to compare them to your vector embeddings. And that operation will return those top K chunks to you, those vectors, and then your user prompt, along with that special information you want it to be returned, gets passed to the LLM, which then generates a larger response, prioritizing what that augmented generation, that RAG data that you've just fed into it. So in short, that's kind of the way that these vector embeddings are used. And since if you have it stored in SQL Server, these operations can hit SQL Server just the way any of your regular application operations are hitting them. And here we are. So now going to vector indexes in SQL Server 2025. It's kind of general availability in 2025. There are things that came before, but for the most part, this is what I'm showing today is basically, the steps from this new learning path on here that we've got for building AI power solutions using SQL Server. And I absolutely, you guys should, if you're interested in this stuff and you're just like, well, can I do AI? Can I do AI in SQL Server? Run through this. It's very accessible. There are some prerequisites that come with it. And so that was why I wanted to kind of show you guys how to do this. And I've got my own data here that I want to try to run and show you guys on. But let's see if it ever finished. I think it did. Yeah. So it took me 44 minutes to embed 22,000 rows, a single column. There's a lot of data in it. And one of the things that I want to show you guys is like, what does that translate to on the back end? Because we are talking about using an AI model. It has to live somewhere. When you're generating those embeddings, it has to actually go ahead and, leverage some sort of that. Let me pull it back up here. That embedding model. And we'll even see that in our code. So that's a part of our prerequisite. So first of all, you may need to turn on some of the preview features. One thing that you're definitely going to have to turn on is the external REST endpoint, so that way you can reference your AI model. There is a way to run it against, not something that's in the cloud. You can host like the Facebook AI with the FAISS embedding model in a container. And in fact, I found on GitHub that there are instances of like Docker files that have SQL Server and the FAISS container right there ready to go. Didn't want to try to run that on my PC while I was doing the demo. Azure SQL serverless is a great fit for what I'm trying to do. So that's what I'm doing here. All this stuff's already pretty much ready to go up there. So that's definitely a benefit. Big thing to keep in mind here as a prerequisite, you're going to need to add an encryption master key and a database scoped credential for your external model. Why? Because you're going to have to use your API key in your external model creation. And so that's where that scoped credential comes in, and you've encrypted it using the master key because you're therefore allowing your logged in user to be able to leverage that API key. I did try to do this with user identity, so that way I didn't have to do any type of API key, but I couldn't get that to work. So, I'm just trying to follow the Microsoft docs as closely as possible for this demonstration, so that way hopefully you guys have like an immediate takeaway. If you try to use the managed or user identities and stuff like that, you have to go in and set that stuff up on the networking of like your SQL Server and whatnot. And if you've ever tried to import data into SQL Server from like a storage container, you may know all about that type of stuff. In which case, let me know if you had insights into how to use that same methodology for the AI generate embeddings. Because yeah, I had to use the API key. Anyways, so once you've got those things in place, it's kind of simple steps here. You identify the data that you want to create the embeddings on, that you want to do your semantic search on. And one thing that you need to know is that when you create that vector index, it's going to have a size here. And I guess I I just have the index. I don't have the create the column on here, but I'll show it in a second. But basically, you create the column, you're going to have to specify the size. That size needs to match the output size of your embedding model. So the documentation uses what's called the ADA2 embedding model. There is a text embedding 3 small, which I haven't tried, which might be quicker and might cost less. But again, I just used what was in the documentation for now. So, you've created that vector column. It has the size that it knows to expect from the embedding model. And then you use this new function called AI generate embeddings to actually populate the vector column. Once your vector, so that takes the data that you're trying to embed, goes to the embedding model, returns your vectors. The vectors get stored in that new column. You create your index on that column. Then you can use vector search on that column. And so that's what I've got shown down right here. You create your vector index, and then when you do your search on the column, and this is what I mentioned about it returning how many nearest neighbors, it's going to do 10. Okay, so let's head over into SQL Server now. And let's see here. What's the data? Yeah, okay. So before I try anything on the Olympic data, I'm going to run through the example that's shown here. So if you go into implement vector data types and vector search, this is where you're going to find this. And so I'm kind of showing how to run this stuff right here, right? Okay. So getting started, I'm going to, think I want to redo this. Maybe I waited too long. Maybe we'll just delete it from here. Okay. Yeah. Let's go ahead and do this one at a time here. I've got more notes over here. All right. So again, first thing that you want to make sure that you do enable preview features if necessary. This is how you enable those REST endpoints. This is how you create your master key. This is how you create your database scope credential. And right here is where that API key goes. There should be in the documentation, it does mention that other, for scope credentials, you can use other identity types, but I couldn't get them to work. I could only get this HTTP endpoint headers to work in this use case, which is probably why they tell you that you need this. Okay, so this is the last prerequisite. So we're going through our prerequisites, and it's to create the external model. Right, so I've already run this on my server, but basically what you're looking for here is your external model. This actually needs to come from Azure in this case, right? And so I'm in Azure Foundry here. I've said I want a new OpenAI model, and I'm told it that I want to use basically the text embedding to deployment, right? So this is kind of like its model type. It's geared towards embedding. And it gives you, right here's where you'll get that key that you need. Thank goodness it automatically blanks it out for me. And then this, which, as long as you've got your networking set up, it's safe to show. It's not like necessarily the most secret thing. It's definitely still behind authentication. But you're going to take that information, where your model is and what the model type is, and that information specifically goes into the location and into the model. And then here's that credential that we had to create up here, right? So hopefully conceptually that makes sense, that within SQL Server, it doesn't do the embeddings itself. It's not an embedding model. It doesn't have like the transformers, the multimodal models necessary to create the embeddings. And so that's why you use something like Azure OpenAI, and that's very common across use for all vector indexes. It does, because you can specify whatever this location is. Like I mentioned, you can host this yourself. This could absolutely be self-hosted. But I get the enterprise data protections anyways of Azure, so I'm pretty safe to be using this, even though I'm still working, organizationally on what's the right way to treat sensitive data, which is kind of why it's nice to have these examples and some test data like the Olympics to work with. But basically, once you've gone through these prerequisites, it's time to try and use your AI embeddings AI generate embeddings function. So we'll go ahead and take this here, and notice that I'm using this model that I've specified in my my external model here. And so I mentioned that we would be able to see what a vector looks like. Kristen, you've got a question? Go ahead and.
Thank you. So what occurs to me is, if I've done all the prerequisites and I've created the embedding model by having to query Azure OpenAI, how long am I going to be able to use that model? If I add a single new line of data in here, am I going to have to go back and get a new embedding, or am I going to be able to use that same embedding essentially for the lifetime of this database?
It's a great question. If the data changes, it needs to go through a new embedding. It needs to go through the embedding model again. And in fact, what I've heard from Microsoft is that at this time, meaning maybe it'll change in the future, at this time, you can't update them. You have to recreate them every time. So maybe what you'll do is, as data changes, hopefully you'll have some tolerance for not needing like real-time search on all of it, or you'll have to implement a way to incrementally do it, right? Because this index needs to get recreated. Even the vector column itself needs to get recreated every time that you need to do these embeddings. And I just mentioned that on 22,000 rows, it took like 40 minutes. So this is still something that, from an engineering perspective, I think everyone's still trying to figure out how to make it available, how to make it like work actually in production, right? It's obviously got, and maybe this is like a good time to pause and just reflect on, like, is all of this worth it? Like, why are we doing this? Like, who cares about semantic search, right? Well, like, in my work, I spent years and years trying to help people build like, data warehouses and Power BI reports that helped decision makers use data in their decisions. And no matter like how much time I seem to spend with report builders and data modelers, it's still tough to do. It's still really tough to get your end user to interact with a report in a meaningful way, or even tell you what needs to go into that report. You know what immediately jumps that problem? A chatbot. If you can go ahead and vectorize your data and feed it back into a chatbot, I have found that end users will immediately engage with one of those over going and looking at a report. Or even if they have a report, they'll just ask the chatbot to tell them what it says. Because it's still this concept of I need to interpret versus somebody is telling me in natural language that I just naturally understand. And that's kind of the trick of all this stuff anyways, is that it's able to tell you what you want to hear, right? And like there's like this probabilistic component of an LLM that's like guessing what you want to hear next. And that's the reason it looks like it works so well and why a hallucination can be so dangerous. But ultimately, we are talking about unlocking a capability that hasn't been possible before. This is driven forward by really three advances. I'm just have you guys staring at all of this vector info right here. Well, at least look at some code, right? But anyways, there's like three advances here that makes all this possible. One, the availability of data. The internet's full of data. We've got tons of it now. Two, GPUs, the availability of GPUs that excel at vector transformations. That's ultimately because we have more data and more ability to do these high dimensional transformations. That's the key, the magic, on top of also some really critical algorithmic improvements. Those three things, though, are really what have made it possible for us now to reliably say, if someone with like a 98% tolerance wants to say, is Pink Floyd like Mozart, right? Now they can do that, right? And so the full text search index, it was never able to get us there because it was only ever able to do these exact comparisons. And in low enough rows, SQL Server will still do those exact comparisons against your vectors. But as we get more and more data, it's just not feasible to be able to keep track of the distances to each vector. And so that's why we have this index that's able to store those vector distances and tell us, in a quick way, how close things are to each other.
Thank you so much for that. There's a lot you hit on there. I know we don't have that much time. I don't want to delay you too much any further,
Sure.
But one quick follow-up, if I could. Do you have any idea what the approximate financial cost is of creating one of these embedding models?
Yeah. So let's run through that really quickly because it can kind of be a maze to figure out, but it's important. And so like one of the things that I wanted to show here, right, is you have this monitor. And so, I did those, I keep forgetting how many it was, but 22,000 rows. My 22,000 rows generated, about 22,000 requests. So that's great. I'm still trying to figure out like how does this translate? Like can a single, and I say rows, but it's actually a column of data getting sent. So it's really like one column value at a time. But it looks like it's and these are biographies. So I'll kind of I have my data here. I can kind of show you guys what it looks like in its raw form. We've got these biographies. So large text, right? Perfect for embedding. So that way, if you tried to do a search to find everyone's whose bio included 13 wins, right? Or moguls, right? That's just like this really weird term that I don't have time to tell SQL Server like how mogul relates to other things. But an embedding model, in the cloud, it has that already figured out because it was trained all using those neural nets and figuring out all of its weights and whatnot, to be able to, when it's fed the word mobile, it can give you a vector embedding that puts it in space that other words that are similar to it will actually mathematically land in a close proximity to them. And hopefully that wasn't a weird word to choose. I just kind of randomly picked. But yeah, so we were talking about cost just very quickly. And the reason I pulled that up was to show you, okay, looks like for each row I got a request, but it wasn't a token, right, per word even. This was 3.13 million tokens. And right off the bat, that makes you think, oh gosh, that seems like a lot. And they give you an estimated cost here, but because I just ran this today, it hasn't returned that cost to me yet, right? But it will, so you can monitor it pretty closely. But one thing that's nice is we can look at our pricing page. Azure does a great job of publishing all their pricing. Sometimes not the most up to date. Like for example, in my case, I'm using something called the ADA2 embedding model. I don't see that here. These are the ones I got. I know I'm not using 3, so maybe it's this one, right? And so if I use that math, so I generated 3 million tokens, right? Times my cost, but that's per 1,000 tokens. So 33 cents. So doing the embeddings is pretty cheap. And this is what you'll find across almost all multimodal model providers, is that they're pretty cheap to run. And that's good because what you're going to find here is that you are doing this a lot. Like, for example, like when you're just going through this, like it's having you hit your endpoint pretty much every time you do something. So for example, it goes through this, rather than worrying about like data that's already there, let's mock up some data and let's talk about like how close, like just as a simple example here, right? So let's copy this and run some of this stuff. Okay, so we're going to declare these vectors and we're going to use that model. We're running AI generate and we're just doing it on 2 examples, Mozart music, Pink Floyd music. And then we're going to insert that into a table that I did delete. So let me get that back. Great. There we go. Any new products, very simple table. I defined the embedding column on it already, although you could, alter your table and add it if you needed to. I got that value of 1536, using some trial and error, but also you just need to match it to what your embedding model says you should expect. And if you choose a different number, SQL Server will tell you you chose the wrong number. It won't tell you what the right one is though. Anyways, so now we've got, this in here. So now we're on the fly generating these embeddings and we're going to insert them in there. Right? Now, let's remove music. Well, that's okay. It doesn't matter. right? We'll just look at it really quickly. We've got these embeddings here, long vectors. Now, let's say that we have a prompt from a client that says, show me products that are in the style of Pink Floyd music. You're just like a classic query, your database has to go find that data on disk. But instead of looking for maybe like the description where it might have to do like a like or it contains, something like that, now what we can do is we can use what's called the vector distance. And this is what I mentioned where you don't need the index. Instead, what this is going to do is it's just going to raw calculate all the vectors. And in this case, I literally only sorted 2 records. So we're not talking anything too tough here, right? So we'll go ahead and do this. And you'll see here, like the values that you're getting, the lower one means a closer distance. And so in this search, if you can imagine this went with all sorts of other types of CDs or other types of products that didn't even have to do with music, it would probably be an increasing distance away from the one that literally said Pink Floyd CD when I looked for Pink Floyd music style, right? So that's just at a basic level showing you this is the conceptually how vector distance works. Now, let's say we move to a table that we have more than 50,000 records. SQL Server can't realistically store all that information. So what we do instead is we create this vector index, which is able to actually, store information about those similarities. And you need what's called a metric. And there are different type of metrics that you can use here. And basically cosine measures the angle between the vectors. So this is ideal for text embeddings. If you were doing something like normalized data, or if you were doing something, actually, I am struggling to think of the examples. The other 2 things that you could do are the Euclidean and the dot metrics. And it just speaks to, we're talking about vector transformations. We're talking about mathematics here. So let's go ahead and create the index, and then we'll run our vector search. And notice we're no longer doing vector distance. We're using vector search. And I'll go ahead and what I should do is turn on my, here we go. Let's rerun this one. Okay, we got this clustered index scan because I got a primary key on there, right? Let's see what happens now if I create the index and run a vector search. Just grab this again. Okay, so we created the vector index. It's letting us know that it used disk ANN. So that's going back to, I talked about the IDF, the hierarchical navigable small worlds, and then we landed on that disk ANN. That's what Microsoft SQL Server chooses. Okay, and now we'll run this. I can highlight everything. And you see now we have the vector index seek, right? So nothing too complicated. We're not talking anything revolutionary here. We're just touching bases about how this is just a new feature in SQL Server that's just like all our other ones. It's just a new index type. We've gotten them over the years. It's all about translating data into a way that the engine can most effectively work with it. We're talking about, not needing to go right to the data every time we have a question. We're going to go to these index pages that stores pointers or information about where everything is at. And I'm still trying to learn a lot about the vector index to understand how much of that analogy follows across, because I'm sure there's a lot of different ways that works. But this is all pretty cool. And basically it does, as we're showing here, it enables us to do quicker semantic search, and we can do it right out of SQL Server. And it also works as a hybrid search scenario, right? So, I think we have rock data in here, right? Yeah. So let's say, for example, there was a lot more records in here, right? So we still want to do a classic filter. Maybe this is a non-clustered index on our category. So that way we're able to take advantage of that. But when we try to go and look into our embeddings to do that semantic similarity search, we can also introduce that. So I don't think I have the non-clustered index on this, so we probably won't see it. I could create it real quick, but we're pretty low on time. So we'll just let it do the clustered index seek itself. I think we need this. Yes. ID, where are you? I'm missing something very obvious here, but I'm struggling to see what it is, and I'm at the end of my demo, so I'm not going to worry about it. Anyways, the whole point of showing this was just that you can combine the vectors. Say that again?
Casing, capital P.
Yeah, it is almost certainly, yeah, but well, casing shouldn't matter in most places, right? Yeah. No, it's saying product ID is invalid because I have a copy and paste issue in here somewhere. But that's okay. I'm not going to worry about it. The most important thing about that is just to recognize that, it's sitting beside our other operations and we can do hybrid search scenarios with it. And so I don't have time, unfortunately, to go through. I wanted to show this on more serious data. I wanted to kind of go through the execution plan and show that when you went over the 50,000 rows, it's going to more effectively use that index. And under 50,000, it's kind of the same because it's, that's that disk AN limit. And yeah, so I am going to continue to refine this talk. This is actually the first time I've given it publicly, so I really appreciate everybody being here today, and I'm definitely open for feedback. But my point was really just to try and, welcome vector indexes to SQL Server and hopefully excite all of you to see what's possible in this new world. And yeah, looking forward to hearing from all of you, any questions you have, and seeing what the community is able to do with this feature.